All right, aloha, konnichiwa, and greetings. Welcome to episode number 1 of the Planets Foundation's Life on Planets weekly YouTube live event. Today our topic is finding life on Proxima B. My name is Kevin Lewis, and I'll be today's moderator for the live event. We're joined by a distinguished group of scientists and professors from around the world who are all members of the Planets Foundation Consortium. We have a simple format for these events. They're roughly 30 minutes in length, and each week we'll connect you directly with the professional astronomers that are creating the technologies and techniques for finding life in the universe. If you're viewing this event live and want to engage with us directly, you can tweet us your questions using the hashtag LifeOnPlanets or email us at hello@planets.life. Lastly, if you like what you see and want to pledge your support to make sure that these Hangouts continue, please visit our Patreon campaign at patreon.com/planets, where your donations will also go to the creation of our telescopes to find life in the universe. All right, so before we get into the discussion, I'd like to give each of you a chance to introduce yourself to the viewers and give a little bit of your background and research specialties. So maybe we'll start with the group here in Maui, Jeff, Mizuki, and Takeshi, if you want to introduce yourself and tell the audience a little bit about yourself.
Sure. So my name is Jeff Kuhn. I'm a physicist by training, and one of the original Planets folks that has been involved in developing some of the ideas that we'll talk about over the weeks to come. My background is in astrophysics right now. I'm a professor at the Institute for Astronomy, University of Hawaii, and I live on Maui.
Great.
Okay. My name is Takeshi Sakanoi of Tohoku University, Sendai, Japan. But I'm now currently staying at Maui Institute for Astronomy, University of Hawaii, staying for 1 year. I'm working on the planetary system in the solar system and also exoplanets. Thank you.
Great.
I'm Mizuki Yoneda. I belong to 3 institutes, like one is the Kiepenheuer Institute for solar physics, and the other one is Tohoku, and last one is University of Hawaii here. And basically, I'm staying in Maui, but I'm working for these 3 institutes, and my field is like planetary science. Yeah, that's it.
Great. And then, Sho, I think we can see you now. Can you hear us? Maybe not. All right, Svetlana, do you want to introduce yourself?
Sure. Hello, my name is Svetlana Berdyugina. I'm a physics and astronomy professor at the University of Freiburg in Germany. And I'm a researcher. I'm researching stars and planets and exoplanets and studying the influence of stars on the planetary conditions and stellar magnetic fields, and searching life on planets with different techniques. Thank you.
Great, awesome. And then, Sho, can you hear us, or are you not able to hear us? Okay,
I
perfect.
can hear.
Hey, welcome.
Can you hear?
Yes, we can hear you.
Okay. I'm Shoichi Okano. I'm Sho Okano from Sendai, Japan. And I'm staying at my home because the typhoon is attacking to us.
Really?
Yeah.
I didn't know that. There's a typhoon.
So,
Wow. This is quite a distinguished and diverse group. You know, we are from Japan and Maui and all the way from Siberia. And no, I think Obara-san.
really diverse. So
Yeah.
we have 12 hours time difference.
Yes, I don't know of a better group of panelists to talk about what we're about to talk about, finding life in the universe. So thank you for all of you for joining us, and I guess we can just get right into it. What was that?
Okay, Obara-san is now connecting, so Obara-san, could you make self-introduction briefly?
Yeah. This is Obara from Sendai, Japan. I'm happy to join this evening. Thank you.
Good.
Great, thank you. Okay, so let's just get right into the discussion. So, today's discussion is about finding life on Proxima B, potentially. And we know a little bit about the planet as far as its minimum mass. It's 1.3 Earth masses. It has an 11.2 day orbit around its star. And it's really close. It's 5 astronomical units to its star. So it's incredibly close. And just to give you a little bit of perspective, that's 8 times closer than Mercury is to our sun. So the first question that we have is from one of our viewers, and he asks, so we found quite a few potentially Earth-like planets in the past, but why is this one important other than it being close to our solar system? What's the significance of Proxima B?
You want to start, Svetlana?
Okay, I can start. I think it's important, of course, because it's around the nearest star to the sun, and we have already quite powerful facilities for astronomical measurements to find out its existence, as it was announced to be discovered a week ago, and continue studying conditions on this planet. The star itself was discovered only 100 years ago, and it is the closest star to the sun, and we see we already for this 100 years learn a lot about its physical conditions. It's a red dwarf. It's pretty cool. It's 3000 Kelvin temperature only, compared to the sun's 6,000 degrees. So it's about twice low temperature. And because of that, a planet which is capable of sustaining liquid water on its surface could reside pretty close, as Kevin said, to the star. And there are many stars, such stars in the galaxy, a majority of stars of this kind. And we also believe that majority of planets we will see will be around these stars. So this is a very good academic and universal example of a planetary system with the most frequent stars in the universe and in the galaxy, and probably most common planets around such stars. So this is a very good example for it, and it's closest to us. So maybe even in the future we can fly over there and test all our speculations, which we have now about it.
Right, which we'll be talking about a little bit later with the breakthrough Starshot.
Right.
So it's exciting.
I think another reason that makes it really exciting, it's kind of like in the old days when we looked at stars and we didn't think that planets were very common. This is almost the first time that we've been able to look at an M dwarf, and so the fact that our first real sensitive measurement of an M dwarf shows a planet is kind of like suggesting that, well, it may be that many M dwarf stars, and like we said, that about 70 or 80% of all the stars in the galaxy are M dwarfs. The fact that the first one that we really had a chance to look at shows a planet, and it shows an Earth-like planet, is a hint, perhaps, that planets are even more common than we ever thought they were from all of the other earlier observations. So I think it's a big deal. I think it's as exciting as the first, almost as exciting as the first detection of exoplanets 20 years ago.
Right. We'll find, time will tell once we start finding more planets around M dwarfs, but it says a lot. Seems like it says a lot just to the probability of planets being around them.
Yeah.
All right. So the technique that we used to find this planet was the radial velocity technique. Can anyone kind of explain a little bit more in detail how we actually execute that technique and how that's done?
Anybody?
Svetlana?
Sure. I give the time to others here.
Yeah, go ahead, Takeshi.
I suggest that the high resolution technique for the infrared range is very important to divide the light signal absorption line, emission line, to the other atmospheric absorption and emission line. So maybe high resolution technique is very important, I guess. And maybe Svetlana, you suggest that the parametry is right?
Well, the radial velocity technique is pretty powerful. We can see variations of radial velocity of a star orbiting the common gravity center of the planet in a star. And by detecting these periodic variations of the velocity of the star, we can figure out that there is something we don't see, actually. And if we measure the amplitude of variations of radial velocities, we see the range of these velocity variations. We can say whether this is a second star or it's a planet. We can determine only the minimum mass from measurements of the stellar velocity, but it still gives us a good limit on a mass of the body. And for the case of Proxima B, that was minimum mass is 1.3 Earth masses, and this is kind of not so bad message. I mean, if you orbit, of course, face on, you can have many orders of the magnitude larger mass of this planet, and maybe not Earth-like at all. We will figure this out later. But for now, it's a very good candidate. So we have to remember this is a candidate for the Earth-like planet with the minimum mass 1.3. If we will succeed at some point, detect spectral lines in the spectra of this planet, if it has an atmosphere or whatever spectral features we can detect, and follow that spectral feature velocity with the orbit, we can measure also velocities of the planet, and then we can say for sure what's the mass of the planet. This is also a possibility to make sure that this is Earth-like planet or it's a heavier planet. So far, we know only a limit to it.
And is radial velocity, is this the best technique that we have to find planets around our nearby stars, or are there other ones that are also, you know, good, or is radial velocity just the best?
No, it's not. There is no the best technique. There is,
Right.
all techniques are really important, especially in combination. So what we cannot verify from one technique, we can find out from another one. And there are several others from measuring photometric variability of a star. If the planet is eclipsing the star, we see transits.
Sure.
And this gives very narrow angle on the inclination of the orbit and allow us to combine these measurements of photometric variability, transit measurements with radial velocity measurements. Then we can say what is the mass and what is the radius of this planet. So this is very powerful combination. And if we add more techniques, as polarimetry, for instance, what I'm doing, then we can get more information on the physics of a planet, on reflective properties, and that already becomes a planetary science, and we have specialists here talking about planetary science. So we can finally, when we combine many techniques together, it becomes already a possibility to study planets themselves as we see them in solar system.
Right. Okay, and then it's kind of a follow-up to that. So what's the next step? How do we actually go about finding life and measuring the atmosphere and doing further science on this planet? I guess I kind of wanted to ask what specific telescopes are we going to be using to try to find life, and what are the specific techniques that we'll be using to do that. Kind of wanted to get an idea just really about the different telescopes that we have to start trying to find life or see if it has life on it.
So the next step from all of these techniques is to be able to somehow separate the light of the planet from the light of the star. And while it's exciting that we now know that there are rocky planets that could have water around M dwarfs, because the M dwarf is so much fainter than the sun, orders of magnitude, the planet, in order to have a temperature that's warm like the Earth, has to be very close to the star. So that means that the separation in space between the planet and the star is very small, and that means that these examples, Proxima B, for example, we aren't going to be able to separate the light of the planet from the light of the star very easily. It's going to take a very big telescope. Even to get the Doppler signals required the biggest telescopes that we have on the ground, operating for several years to detect that Doppler signal that was the evidence of the planet. And the Doppler signals are never going to tell us about life. So the next step for all of this is to use techniques that allow us to separate the planet light from the starlight, and that's a big telescope. And the Planet's Foundation and the scientists that you see here have all been working on those technologies to be able to produce telescopes that don't scatter light, and then to produce techniques that allow us to actually make images of the planet by using, for example, the rotation of the planet around the star. So we know that with something, the telescope not too much bigger than the biggest telescopes that we now have, we could make an image of the surface of the planet of Proxima B. But it would take something slightly larger than the biggest telescopes on the ground that we now have. But that's what this group is all about, is developing the technologies and the algorithms that will allow us to move in that direction.
Right, yeah, that makes sense. Because I read something that's saying that, you know, the EELT, or the Giant Magellan Telescope, would be able to directly image Proxima B. I don't know if that was accurate or not, but you know, there's some ideas that.
Yeah, so the Giant Magellan Telescope is about 25 meters across, and the EELT is about 40 meters across. And the biggest telescope we now have is the Keck telescope. It's about 10 meters across. I don't know whether those big telescopes will actually be able to do this problem. They have to control scattered light at a level which is pretty remarkable. But it's something that we look forward to. We'd like to see telescopes that are specifically designed to solve the exoplanet problem and to look for life. And they look a little bit different than the TMT or the EELT. Those are examples of telescopes that we call Keck-era telescopes. Their mirrors are derivative of the designs of the Keck telescope, which have many, many pieces of mirror that are all joined together. And they're great for doing problems related to, well, astronomy that requires a field of view that could, for example, see many galaxies or solve many other problems in astrophysics. If you give up on the large field of view, then we can build telescopes that can do much better for the exolife and the exoplanet problems.
And I mean, can we talk about that a little bit? Do you want to talk about the Colossus and what that's?
Kevin.
Yes. Go ahead, Sho.
I have no headset, so the sound is not good. So let me say something about Proxima Centauri B.
Yeah, please do.
Even if it is in habitable zone, that is very vague idea. So the important issue is whether the planet has atmosphere or not. For instance, the Earth's surface temperature is only minus 16 degrees Celsius, even if the Earth has no atmosphere. And the Venus in our solar system is inside the inner edge of habitable zone. But the Venus has surface temperature of more than 500 °C. And so the important issue is if the planet has atmosphere or not. And
Right.
Svetlana has already developed technology to detect atmosphere of the planet. So even the telescope diameter is small, like Planets telescope, step 1 Planets telescope. I believe we can detect the planetary atmosphere with Planets telescope.
Okay, that's great. I didn't actually know that. That's interesting.
I'd like to continue a little bit here also. That, of course, atmosphere is very important, as Shaw pointed out, that, for surface temperature. But what is also interesting about the system is stellar activity. That this M dwarf, although it's not so active as many others, other M dwarfs, but much more active than Sun. And for instance, when star spots go across the disk, so there is this dark regions of magnetic fields there, light of the star changes by 17%. And this is in contrast to the sun, where we see changes of 0.1%. So this is 170 times larger radiation input on a planet variations compared to the sun. So imagine that every 80 days, so rotational period 80 days, you have variations of a few percent or up to 15–17%, between 10 and 17% variations of the brightness of a star illuminating the planet. So this heat and variations on the planet is so large that climate variations and weather variations would be enormous. So this is also a very important factor we have to take into account when we talk about habitability, that life has to adjust itself to these dramatic changes of the weather on this planet.
Right.
But we can go back to telescopes. Maybe that's what also exciting, how we can see that. With bigger telescopes, with smaller telescopes, we can see whether there is a atmosphere or not. We can study some variations in reflectance and see if there are clouds or so. With bigger telescopes, we can get much more information about this planet.
Sure. Great. All right, and then Jeff, can you talk a little bit about the breakthrough Starshot and potentially traveling there? I know a part of the press conference, part of that was, his name just slipped my mind, but talking about actually sending space probes there. Is that realistic? Is that something that can actually happen in the next 50 years? I mean, what are your thoughts on that? I know you're part of the committee.
In some ways, it's kind of like we're at that stage when Jules Verne was talking about how to get from the Earth to the Moon. Remember his vision was a giant cannon that he could launch early astronauts from the Earth to land on the Moon. And you know, ultimately we don't know exactly how the technology will work, but we're talking about some of the same ideas. And in this case, it's a laser that's about 100 gigawatts of power, and it runs for a couple of minutes. And during that time, it accelerates a probe, which might weigh only a few grams, from basically a low Earth orbit with an acceleration of about 60,000 Gs. That works for about 2 or 3 minutes. And that probe can be accelerated just from the pressure of photons up to a velocity of 20% of the speed of light. So we can get that, if we can get that to work, and we can get it in a way that we can point it directly at Proxima, or actually where Proxima will be. Proxima, over the 20 years that it takes to get it's roughly four light years away. During that time, the apparent position of Proxima actually moves a bit. So we have to point it ahead. And if we know how long it takes to get there, then we can get it to pass by Proxima, and we can take pictures in a little tiny camera and send back a signal using that same big reflecting dish that was the sail that captured the laser light. And we can send probably enough information to get an image of the planet. That's the idea. But it's certainly true that we don't. Somebody needs to mute their sound.
I couldn't quite hear that last part, but
someone has joined us. They have to mute their sound.
Yes.
I don't know who it is.
We all have to mute when we don't talk.
Anyway,
okay,
the answer to your question is that yeah, it is possible. It's going to take a bunch of people working on solving many hard technical problems, but this group is convinced that it is possible, and that we have to start now if we're going to do it. And the discovery of Proxima B is really exciting, because it means there really are interesting and important targets that are within reach in a human lifetime.
right. Okay. Yeah, it sounds. I mean, it's a fascinating idea, and I hope it succeeds, because actually being able to send spacecraft to near stars within a human lifetime is it's a great idea if that actually happens. All right, we're almost at our half-hour mark. Does anyone have any final thoughts or comments on our first Planets Foundation hangout?
Well, I'd like to add that actually we always underestimate our capabilities with the instruments we have. And what happened in the past, that we dream about far distant future, what we can learn about this planet with the future instruments. There are always smart people who figure out how to use the instruments we have already to learn more. So as we will approach that flight, I guess, to interstellar flight to Proxima and Alpha Centauri in general, I guess we will know a lot already about this planet, and this is what we will focus right now to learn about this planet, and start searching life on this planet already from today.
Right. Good point. All right. Well, thank you everyone for joining. Appreciate your time, and thank you for anyone that's tuned in live to this. You can, if you want to watch the archived session of this hangout, it's at planets.live/events, and we will be trying to do these every week, every Monday at 5 o'clock. The time might change, but hopefully we will see you next week for episode number 2 of the Planets Foundation Life on Planets Weekly Hangout.
Okay.
Thank you.
Thank you.
Thank
Bye.
you.